In the previous two videos, we were introducing material about the switches and the various components which go inside the power converter. Now, this rule, we have been building up to this rule, and we are talking about that we need to have a rule which governs the formation of these circuits. That is, how should we connect these switches and the inductors and capacitors in order to make a valid circuit. So, that rule that we will refer to and look at right now is called the rule of interconnection. In short, it is called the ROI. Now, this rule very specifically states where one can connect a switch in a converter circuit and where one cannot. So, it is about where you can connect a switch, it is not about where you can connect inductors and capacitors. In a standard linear circuit, you can connect them pretty much the way you want, but in case of a switch mode converter, you have to be extra careful where you place the switch. So, this rule basically tells us exactly that. Now, before stating that rule, two terms needs to be clarified, and we'll as it's shown there, these two terms are voltage stiff and current stiff. Now, from the name itself, it appears it kind of indicates what they mean. Voltage stiff elements are those which do not allow the voltage across them to change suddenly or in a discontinuous manner. Examples would be, for example, a voltage source or a capacitor. Capacitors, we have already seen the equation. Voltage source is by definition an ideal voltage source, does not allow the voltage across it to change irrespective of the load or the external conditions. So, these two elements are typical examples of voltage stiff elements. On the other hand, current stiff elements are those, it is just the dual of it. It says those are elements which do not allow the current through them to change suddenly. Now, examples of those would be a current source. An ideal current source, as you know, has infinite impedance, internal impedance, and irrespective of what the external load is, the current obtained out of a current source never gets affected by the external conditions. Now, the other example, as we have seen, the physical passive element is the inductor. So, an inductor does not also allow the current through it to change abruptly. Now, this rule of interconnection says that if that switch, remember we had that switch on one side, it had the node A, and on the other side it had node B. So, it says if node A is connected to a current stiff branch or element or node, the node B cannot be connected to a current stiff branch. And okay, so but if the node A is connected to a current stiff branch, then the node B can be connected to a voltage stiff branch. Just conversely, if the node A is connected to a voltage stiff branch, node B can be connected to a current stiff branch, that is allowed. Whereas, if node A is connected to a voltage stiff branch, node B cannot be connected to a voltage stiff branch. So, that is in short, you can connect dissimilar stiffness properties of nodes through a switch. So, if I want to summarize the whole table. Okay. So, so that is what the rule of interconnection says. Now, let us see how we can use this rule of interconnection to get a few circuit configurations, few examples, and get a slightly clearer idea about what these current stiff and voltage stiff elements or branches could look like. So, that is a current stiff element. Also, likewise for the voltage stiff, let us consider a capacitor. Okay. Now, the current stiff element says that the current through it cannot abruptly change, and the voltage stiff elements property is the voltage across it cannot abruptly change. So, when I talk about current stiff properties, more than a node property, it looks like a branch property. Okay. So, I will talk about a current stiff branch. So, what other further examples of a current stiff branch could there be? Now, these I won't really prove that these are current stiff branches. I would rather leave it to you to prove that these are indeed current stiff branches. Okay. So, this is one second example of a current stiff branch. All of these are current stiff branches. So, now let us look at a few voltage stiff branches. That is one. Okay, let that would be a third example of a voltage stiff branch. Now, in the earlier case, we just in the previous slide we were talking about voltage stiff nodes and current stiff nodes, and suddenly we switched over to voltage stiff branches and current stiff branches. Now, whenever we have because the switch has two nodes, so we have to connect the nodes of the switch to some nodes of a particular element or a particular branch. So, both these nodes across the current stiff element would qualify as current stiff nodes. Both these nodes of a voltage stiff element would also qualify as voltage stiff nodes. Okay. So, having said all that, so let us see how we can formulate some of the basic converter circuits. Now, before again we need to do one more little exercise. As you can see, as you can fairly well appreciate, that if you put a simple switch in series with an inductor, the moment the switch turns off, you go into a discontinuity. Now, that, as we have so often previously emphasized, that is not something that we are going to allow in the circuit. So, so we create a construct where we allow a possibility for the inductor current to flow irrespective of what the switch position is. So, right now this particular construct that we have is called the single pole double throw, but the name itself is very clear what is where the pole is, that is where the pole is. So, this is where the pole is, and throw the first throw is T1 and the second throw is T2. Now, all the SPDT nodes are connected to some circuit nodes. So, that is the way we are going to construct the circuit. With what this statement means is that neither this pole P nor this throw T1 or this throw T2, none of these three nodes are going to be left hanging open. Okay? They will be connected to some node in the circuit. That is point number 1. Point number 2 is no two nodes in this SPDT construct are going to be short circuited. So, that is the second condition that we will impose while we are constructing the circuit. Now, why are we imposing the second condition, you might ask. See, if we short P and T, then there is P and T1, then there is absolutely no point in having the switch switching away from T1. So, if the switch goes from T2 to T1 and then from T1 to T2, when it goes from T1 to T2, one would expect that the connection between P and T1 is disrupted, is opened. But if you already P and T is short, these two are shorted, then that is not going to happen. Okay? So, therefore, and you can take a combination of any of these three, any combination of 2 out of these 3 nodes and verify for yourself that if any 2 of these nodes are shorted, then the function of the switch is kind of lost. Okay? So, the second statement is kind of stating the obvious, but I thought that let's bring it out. Let's be very clear about that statement. Okay, so using that SPDT switch, those are the 2 constructs which we come up with. The first construct is the inductive switch cell. Okay. So, what does the inductive switch cell do? And that is one of the motivations why we took this SPDT. So, to the pole of the switch of the SPDT switch, we have connected the inductor or the current stiff element. So, instead of an inductor, it could have a whole jing-bang combination of current stiff branch, but right now we are considering let us have just an inductor as a representative current stiff element. The advantage of having this, or the significance of having connected the inductor to the pole of the SPDT switch is that the inductor current is never interrupted. Point number 1. And point number 2, just from the rule of interconnection, if you recall, this is a current stiff node. So, if one has to obey the rule of interconnection, then both nodes T1 and T2, both these 2 nodes have to be voltage stiff. So, that is what the statement says. If you are using a inductive switch cell to form the circuit, the converter circuit, then the inductive element or the current stiff element should be connected to the pole of the SPDT, and nodes T1 and T2 must be terminated in voltage stiff nodes. Okay, that is the first condition or the first construct using the SPDT, the inductive switch cell. You can also have a capacitive switch cell, where the capacitance or the voltage stiff element is connected between nodes nodes T1 and T2. So, see that irrespective of which position the switch takes, if the switch is in T1, the capacitance is not shorted. If the switch is in position T2, then also the capacitance is not shorted. So, just by operating the switch, within the switch there is no question of violating the ROI. Now, if we have to satisfy the ROI for the rest of the circuit, what we definitely must ensure is that any of the nodes, but not all the nodes, not all the 3 nodes, any of the nodes must be connected to a current stiff branch. That is the sufficient condition to ensure that ROI is satisfied when one is making a circuit using a capacitive switch cell. Okay, so these are, we are now armed with basically two weapons, one of these, or rather tools. The first tool is the inductive switch cell and the second tool is the capacitive switch cell. Now let us see what we can do with that. In order to look at that, circuits. Now before, again we need to do one more little exercise. As you can see, as you can fairly well appreciate, that if you put a simple switch in series with an inductor, the moment the switch turns off, you go into a discontinuity. Now that, as we have so often previously emphasized, that that's not something that we are going to allow in the circuit. So so we create a construct where we allow a possibility for the inductor current to flow irrespective of what the switch position is. So right now this particular construct that we have is called the single pole double throw, but the name itself is very clear what is where the pole is. That's where the pole is. So this is where the pole is, and throw, the first throw is T1 and the second throw is T2. Now all the SPDT nodes are connected to some circuit nodes. So that's the way we are going to construct the circuit. With what this statement means is that neither this pole P nor this throw T1 or this throw T2, none of these three nodes are going to be left hanging open. Okay, they will be connected to some node in the circuit. That's point number one. Point number two is no two nodes in this SPDT construct are going to be short circuited. So that's the second condition that we will impose while we are constructing the circuit. Now why are we imposing the second condition, you might ask. See, if we short P and T, then there is P and T1, then there is absolutely no point in having the switch switching from away from T1. So if the switch goes from T2 to T1 and then from T1 to T2, when it goes from T1 to T2, one would expect that the connection between P and T1 is disrupted, is opened. But if you already P and T is short, these two are shorted, then that is not going to happen. Okay. So therefore, and you can take a combination of any of these three, any combination of two out of these three nodes and verify for yourself that if any two of these nodes are shorted, then the function of the switch is kind of lost. Okay. So the second statement is kind of stating the obvious, but I thought that let's bring it out. Let's be very clear about that statement. Okay. So using that SPDT switch, those are the two constructs which we come up with. The first construct is the inductive switch cell. Okay. So what does the inductive switch cell do? And that's one of the motivations why we took this SPDT. So to the pole of the switch, of the SPDT switch, we have connected the inductor or the current stiff element. So instead of an inductor, it could have a whole jing-bang combination of current stiff branch, but right now we are considering, let's have just an inductor as a representative current stiff element. The advantage of having this, or the significance of having connected the inductor to the pole of the SPDT switch is that the inductor current is never interrupted. Point number one. And point number two, just from the rule of interconnection, if you recall, this is a current stiff node. So if one has to obey the rule of interconnection, then both nodes T1 and T2, both these two nodes have to be voltage stiff. So, that is what the statement says. If you are using a inductive switch cell to form the circuit, the converter circuit, then the inductive element or the current stiff element should be connected to the pole of the SPDT, and nodes T1 and T2 must be terminated in voltage stiff nodes. Okay, that is the first condition or the first construct using the SPDT, the inductive switch cell. You can also have a capacitive switch cell, where the capacitance or the voltage stiff element is connected between nodes nodes T1 and T2. So, see that irrespective of which position the switch takes, if the switch is in T1, the capacitance is not shorted. If the switch is in position T2, then also the capacitance is not shorted. So, just by operating the switch, within the switch there is no question of violating the ROI. Now, if we have to satisfy the ROI for the rest of the circuit, what we definitely must ensure is that any of the nodes, but not all the nodes, not all the 3 nodes, any of the nodes must be connected to a current stiff branch. That is the sufficient condition to ensure that ROI is satisfied when one is making a circuit using a capacitive switch cell. Okay, so we are now armed with basically 2 weapons. One of these, or rather tools, the first tool is the inductive switch cell and the second tool is the capacitive switch cell. Now, let us see what we can do with that. In order to look at that, so what now we are going to look at is how we can formulate a circuit using those constructs. In any power converter circuit, I mean these are called non-isolated, and I will just explain what that means. But in any power converter circuit, the bare minimum that you expect is a source which will give the energy and a load which will take the energy. Okay. So, those are the bare minimum requirements, and they must be connected, of course. I mean, we are not doing wireless power transfer, it is a it's absolutely a galvanically connected circuit. Yeah. So, therefore, there must be the source and the load must be connected to each other. Now, if the source and the load share the same reference potential, okay, then such the corresponding circuits are called non-isolated. That means there is always a common potential between the source side and the load side. Okay. So, that common potential here is what is called, what we have termed as the node G. I mean, some people call it the ground, some people call it the reference earth, whatever, neutral. This is just the reference potential, we will call it the ground. Now, to the left we are considering our voltage source, because that is the most common thing that we see in real life, and this is a load. We are not really specifying the load, but most of the loads that we see in DC-DC, they require a particular voltage to be maintained across it. So, actually we although we have not stated it, these loads by some means are made voltage stiff or are required to be voltage stiff. Now, normally the way it is done is, if you place a capacitor across the load terminals, you give that voltage stiffness property. Now, okay, more about that later. So, let us talk about how we formulate the basic converters. Yes. So, this is one of the constructs that you see on the screen, and we have just rotated this inductive switch cell in a particular way, and we see that we can connect once we make these connections, the corresponding circuit looks very interesting. Yeah. So, we have the source terminal straight go into the inductor, and then we have the SPDT switch, and then there are the load terminals. So, the load is connected as shown here. So, if we just take the node names that we had there, and since we said that we want normally the load terminals are made voltage stiff, so we will just show the capacitance there. Now, I really do not know what this converter is going to do. I really do not know yet, but we just get a structure. We get some structure. Now, let us see whether we have the only rule we know so far is the rule of interconnection. So, let us make sure, convince ourselves that we have not violated it. So, this is a current stiff element in series with a voltage stiff element. So, this entire branch essentially becomes a current stiff branch. Okay. Now, when it is connected to node, let us say we call it T1 and we call this T2. So, when the switch is connected to T1, the current stiff node is connected to ground. Now, you might wonder like what should be the stiffness property of the reference node. Now, by definition, the reference node is not considered to change. Its absolute potential might change, but we have always considered that to be the reference. So, therefore, its potential, whatever it might be, we always consider it to be 0. I mean, that's fine. There is no theoretical conflict with that consideration. So, T1 or the node G is essentially behaving like a voltage stiff node. Okay, its potential I mean its potential difference with respect to itself does not change. So, it's a voltage stiff element, it's a voltage stiff node. And T2, just because of this presence of this voltage stiff element here across the load, T2 also is another voltage stiff node. So, irrespective of whether the switch is connected to T1 or T2, the current stiff element is always connected to a voltage stiff node. So, ROI is satisfied. So, let us see what other combinations we could have. So, let us see the next one. In the next one, we have just flipped around the inductive switch cell, and sorry, I will use a different color. Let me erase it and use a different color. Yeah. So, what does this this combination of particular switch cell orientation and the circuit primitive, this combination, what converter does it give us, or what topology does it give us? So, let us see that. So, you have the node S here, these are the two throws of the switch, that is the node G here, that is the pole of the SPDT, the inductor is connected here, and the load terminal, those are the two load terminals. One of the load terminals is at the reference potential and the other is the node L. So, again let us see whether we have satisfied ROI. Again I am saying that we still do not know what this converter does. We have to see, we still do not know how to make it work, but we have just got a structure, we have a rule, we are just trying to make sure that a rule has not been violated. Okay. So, we have a current stiff branch here. So, this node is a current stiff node. When the switch switch is connected to node S, note now that the node S, that this particular throw T1 of the switch is now connected to a voltage stiff node. Okay. So, when the switch is connected to the throw T1, then T1 is now a voltage stiff node, whereas and also when the switch goes to throw T2, it is connected to the node G, which is another voltage stiff node. So, again the current stiff node in either position of the switch, it is connected to voltage stiff nodes. ROI is satisfied again. Okay, great. So, we have arrived at two structures. Okay. Now, is there another possibility? Yes, there is, because there are three, you can consider that there are 3 slots and 3 items to fill those slots with. So, the number of unique combinations that you can get are would be 3. Okay. So, the third option is in front of you, and so this is how these connections we will go ahead with, and therefore, the corresponding converter so that is the load, and that is again that capacitance which made the load node a voltage stiff node. So, here again we have the node L, the node S, and here is the node G. So, let us now see where we have connected the switch, because as you might recall, we had said that the ROI is a rule which says where we can connect a switch in a converter circuit. So, the switch, the pole of the switch has been connected to a current stiff element. So, let us now convince ourselves that these two nodes T1 and T2 are connected indeed to voltage stiff nodes. Now, if you look at this circuit, it is absolutely clear that both the nodes T1 and T2 are voltage stiff nodes. Great. So, ROI is satisfied. Now, if ROI is satisfied, so what we would like to believe is that we have got working circuits, but we still have no clue how to make it work. We have got a circuit which stands, it looks at us and says that okay, there was a rule which we logically derived again, and all these 3 circuits satisfy that rule. Now, how do we operate them? So, let us see few things about their operation. Yeah. As you know, the first time we look at a new entity, we first try to understand how this is supposed to behave, okay, how it normally behaves. Now, that question I am just specifying explicitly. Okay. how does it usually or normally now these are in normal spoken English, these are fairly well understood terms. When I say what is the usual weather of Kanpur, you will say either it's never wet, it's usually dry. Okay, that's the usual weather of Kanpur. Okay, and what's the usual weather of let's say Srinagar, then you could say that it is cold to moderate. Okay, so these are the usage of these words are very well understood. But when it comes to an engineering entity, we need some more clarifications. Now, usually when we say when we use the word usually and normally, inherently or without knowing kind of inside us, we tend to refer to the steady state behavior of a particular engineering entity. So, basically we are trying to find out in steady state how do these converters, how do we make it work. Now, one thing is for sure, okay, the voltage source will have to have a voltage, and the switch just by definition it will have to turn on and turn off. Now, just it cannot turn on. If it turns on and off randomly, then we do not get anything useful out of it. So, we have to first decide how we are going to operate that switch. Now, to do that, we will define something called a okay, let's a switching function. The switching function says, okay, for a certain duration of time, so it is a function of time, and arbitrarily let us assign that when the switch is in position T1, we will give it a 0, or maybe we will give it a 1, T1, okay, fine, that is the first one. So, we will assign a value of 1, and in T2 it will assign a value of 0. So, when the switch is in position T1, we will say that the switching function is 1, and when the switch is in position T2, then we will say the switching function is 0. So, here it is T1, here it is connected to T2, and so on. Okay. Now, when I say so on, I am actually not saying something very important. So, let me say that whenever we talk about steady state of any system, we have this inherent idea that maybe the circuit went through some change, but after that change happened, the circuit has come down to a new state or condition where all the variables are more or less or practically constant. Okay. Now, in a switch mode circuit, that constant thing, that exact definition of constant does not hold correctly exactly. Okay. That is because the switch, this switch here is the element, just by its very nature, it is always supposed to toggle between these two positions. Now, if it keeps on toggling between these two positions, you would expect the voltages and currents applied to various parts of the circuit to constantly change with time. So, that definition of steady state where variables are constant does not really apply to a switch mode circuit or to a power electronic converter. So, what is the new definition or the sensible definition of steady state when we are talking about power converters? Now, that definition says that or understanding is, as long as the value of any particular variable in the circuit at an instant t0, let us say it is bounded. Okay. It has to be bounded, because you cannot say that okay, the circuit after a change, it's a particular variable became known and it became constant at infinity. Now that completely is an insane statement, because if the variable is infinite, then it has not really become that is not a steady state, that has gone out of bounds. So the variable it must be bounded. Okay. Now that is the first condition, and the second condition of a steady state is, if we know the value of the variable at an instant t0, then the value of the variable after a certain arbitrary interval of time should also be known. Now, this statement looks exactly similar to that of a a statement of periodicity. Okay. Now let me just explain under what condition it becomes periodic. This statement does not necessarily mean that it is periodic, because I have not said that this variable capital T here is a constant. I have not said that. So until I say that T is a constant, it really does not become periodic. But we will see that effectively in a very simple mode of control of this entire converter is when we actually make the system periodic, so that the system becomes quite a bit predictable. Now in order to do that, what do we have to do? What we have to do there is to make sure that this cycle, that look, the switch is operating as a cycle. In the first interval it was connected to T1, in the second interval it was connected to T2, in the third again T1, again T2, and it will go on and so on and so forth. So basically this connection to T1 and T2 comprises the two intervals in which the switch can exist. And if this switch circuit is supposed to work, then it has to keep toggling between these pairs alternately. Okay. So T1, T2, T1, T2, it has to repeat in that sequence. So if we take that pair T1, T2, the time that it remains in this total, over this total pair T1 and T2, we will call this, we will give it a name. We will call it switching period. Now in the switching period, the interval for which the switch is in position T1 and the interval for which the switch is in position T2, those could vary. But if we choose a mode of operation where the switching period does not change, then we can, in that case, we can refine our definition of steady state, saying that the value of any variable, now this f could be a voltage at this node, or a, let us say, the current through this particular node, through this particular branch. It could be any variable in the circuit, any. Now any of those variables will follow a periodic law as shown. This periodic law applies to any variable in the circuit in steady state. Okay, any variable in the converter, switch mode converter circuit in steady state. So let us take f is equal to Okay. So, I have just replaced f with IL, yeah, IL, okay. So, I have replaced f with IL. So, this is what is supposed to happen. Now, let us dig a little bit into the inductor and try to find out what this implies. Now, if you look at the inductor, then IL, as we have seen, the integral form of the equation is equal to 1 by L VL, which is the voltage across the inductor dt. So, this is the indefinite integral. So, if I now find out delta IL from a t I mean instant of time t1 to another instant of time t2. So, what I will have to do is I will have to take the definite integral from t1 to t2 of VL dt. Okay. So, this is what I have to do. Now, I know that that if it has to be in steady state, then this property, then this relation must hold. Okay. Now, if I substitute T1 is equal to T naught and T0 plus, or rather T2 is equal to T0 plus Ts, then the left hand side, so of this equation now becomes and this difference, the difference between IL and T0, IL at T0 plus Ts and IL at T0, that has to be 0 in steady state. So, let's write that relation once very clearly. So, this is equal to 0. Remember under what condition, and that is very, very important to remember, that is now if I just get rid of the quantity in the middle, this integral on the right should equate to 0 in steady state. Now, this is one integral scaled by a constant, which we know that it is not infinite, it is a finite inductance. Okay. It is neither 0, it is definitely not 0, and it is not infinite as well. So, since it is bounded, what we get now is a condition incidentally. So, we will change the now the appropriate limits of T1 and T2. So, the limits now become T0 to T0 plus Ts. Look, what does this equation in the box tell us? That the integral of the inductor voltage over one complete switching cycle in steady state should be equal to 0. Now, if the this statement is necessary and sufficient for a steady state in case of the inductor, that if the inductor is in steady state, then its integral, then the integral of its voltage over a complete switching cycle is 0, and conversely, if the integral of the inductor voltage across one switching cycle is 0, then the inductor is in steady state. Okay? So, this particular law is called the flux balance condition. That is because you know that the integral of the voltage dimensionally is equivalent to flux. So, it is now it is also sometimes referred to as the flux balance condition. Remember, that is one of the conditions to detect or to qualify an inductor is in steady state. For the capacitor, it is there is just a dual of this relationship, and I am not really going to going through all those the same arguments once again, but in case of the capacitor, the same law is called the charge balance condition, and there instead of the voltage, what we need to integrate is the capacitor current. So, this is the condition which tells us that a capacitor is in steady state, or if we know that a capacitor is in steady state, then this condition must be true. Okay? So, we will use this flux balance and charge balance conditions to find out the steady state behavior of some of these circuits. So, we will okay, good. So, we will give a few names. So, we will say that the source voltage is Vg, and the output voltage or the load voltage is Vo. The reference polarities are as shown. For the voltage source, it is given, and the reference current direction in the inductor, that is also shown. Okay. So, for the inductor, the reference voltage polarities are also shown. See that the voltage polarity for the inductor and the current direction, reference current direction in the inductor, they conform to what is called the load convention, and we will use this load convention right through the circuit for marking, indicating the reference voltage polarities and reference current directions to through any circuit element. Okay. So, let us see what happens when the switch is in T1. Okay. So, VL is equal to so in T1 VL is equal to Vg, and when the switch is in T2, then VL is equal to here is Vg, and there it is Vo. So, it is Vg minus Vo. Now, the flux balance condition for the inductor said that the integral of this voltage, inductor voltage, over this entire switching cycle will be 0. So, let us say that this was we call this arbitrarily, we call this duration T on, and we call this duration T off. This is arbitrary. I mean, you could just change the names, interchange the names, and nothing really changes. So, what the flux balance condition says, Vg multiplied by T on plus Vg minus Vo multiplied by T off is equal to 0. So, see that was the inductor voltage due in the T on interval, and this was the inductor voltage in the T off interval. We are just taking, and these are, we are considering that Vg was a constant, Vo is a constant, they do not change much. So, therefore, the integral is just taking the value in that interval multiplied by the length of that interval. Okay. So, this consists of two parts, this integral, and let us see what is the net result of it. So, I will collect the terms corresponding to Vg and so equal to now see that Vo, if you look at the right hand side, Vo is never going to be less than Vg. The minimum value of Vo that you can have is when T on is 0. For any other non-zero value of T1, Vo is greater than Vg. So, for this particular reason, the voltage is always seen to go up, and therefore, this converter is called the boost converter. Okay. Now, normally this is written a little bit differently, and that is because we define a quantity called duty ratio D, and that is defined as T on upon T on plus T off. And this would so this is what the ratio between the output voltage and the input voltage, that is what it turns out to be. It can be very succinctly expressed in terms of this quantity D, which is the duty ratio. Okay. The other converters. So, we will go ahead and apply this rule sequentially. So, again before doing that, we have to mark the reference directions. So, that is IL, and correspondingly once we arbitrarily decide the current direction, the corresponding voltage polarity is defined by the load convention. So, once that is done, so let us use the same symbols here, VO, the similar polarity. So, T1, T2. So, when the switch is in position T1, VL is equal to Vg minus V naught, and when the switch is in position T2, the VL is minus V naught. See, the minus sign comes out here. The switch is in position T2. So, this node and G is shorted, the pole and the node G is shorted. So, therefore, this minus sign comes up here. So, the reference potential, the positive reference potential is connected to the negative of VO. So, therefore, VL is equal to minus VO. Okay. Now, this is one interesting part. This is where to assign the signs of each one of these quantities. It is essential that you look at the circuit carefully before you put this plus or minus signs, because this is one place where students get make a lot of mistakes. Yeah, they get a little confused. So, don't do it. It's pretty straightforward. Just follow this sign around. If the plus sign comes on to the reference plus sign, then the corresponding voltage is positive. If the minus sign comes on to the reference plus sign, then the corresponding voltage is negative. Okay. So, use the straight up and do not get confused ever. So, let us use the flux balance condition again. So, here you will find that it is Vg minus V naught into T on plus I am using plus in a very generic sense. So, in the T2 on the T off duration, the voltage VL is minus V naught. So, that is T off equal to 0, that is the flux balance condition. Now, again if we rearrange terms, so we get Vg T on and we take V all the VO terms on the other side. So, we get T on plus T off and VO by Vg is equal to voltage could be okay. The second thing, note that that's pretty cool. This this quantity, by the way, is sometimes denoted for the as and okay, as a voltage gain. The maximum value of the output voltage, it could possibly be Vg, it cannot be more than that. So, and that only happens when T off is 0. So, which is kind of an unusual situation, which says that you have kept the switch always in one particular position, which is completely which does not happen really. So, in the normal case, when T on and T off are both non-zero, so what you would get is the output voltage is generally lower than the input voltage. For such for this particular reason, this converter is called buck. The voltage, output voltage is bucked, it is reduced. Okay. So, that is where this converter gets its name from. And let us look at the third option then. Now, we'll apply now, we do not need to so those are the reference polarities and reference directions, and those are the reference input and output voltages. Okay, so let us look at what happens to the inductor voltages. So, when it is in position T1, VL is equal to Vg, and when it is in position T2, VL is equal to V naught, pretty simple. Okay. So, again let us apply the flux balance condition and we just go straight after it. And then rearrange terms to get VO we take onto the other side. Okay. A few things about this converter. Till now we saw that the output voltages for the buck and the boost converter, they were the output voltages, actual output voltages were in the same polarity as the reference polarity. Okay. But in case of this particular converter, we still do not know what its name or property is, we see that the output voltage that we obtain here, they are reversed, the polarity is reversed. So, now when you actually put a, let us say a voltmeter, if you put a DC voltmeter and put the reference point here and the measuring point here, and you have a voltmeter, then this voltmeter will give you a negative reading. So, now that's the implication of this particular equation, right. So, that's the first implication of this equation. The second implication is that, look, when does this output voltage become equal to the input voltage? Obviously, when T on equal to T off. If that happens, then VO becomes equal to VG. Now, when now T on becomes equal to T off, that corresponds to a duty ratio of 0.5, because the T on is just exactly equal to half the total switching period. So, at D equal to 0.5, the magnitudes of the output and the input voltages are equal. What happens if T on is increased further? See, as T on is increased further, for example, if T on is equal to 0.75 of Ts, then T off is forced to be 0.25 of Ts, and this particular AV is then becomes 3, or rather minus 3. So, that means now the output voltage keeps on increasing and starts going beyond the supply voltage. Whereas, look at the other end, if the on time or T on is reduced below 0.5 Ts, then the output voltage
becomes monotonically lower
as compared to Vg. Okay. So, this particular converter, what it does is, it is able to increase the output voltage magnitude greater than the supply voltage, and it is also able to reduce the output voltage below the supply voltage. So, it does both buck and boost. So, this converter is known as the buck boost converter. Okay. So, these are the 3 basic converters. There is one more, and we are going to see that converter when we start off with the capacitive switch cell. So, that is going to come in the next video. For any questions, just wait till the discussion hour that we are going to have on Wednesdays, and ask all your questions, direct all your questions to me, and you already have my email address in the first video, and I guess in the handout. You can also feel free to send an email. I will be there to answer your queries. Okay? Thank you very much.